So recently we've done some videos on the channel where we evaluate integrals using Fourier series as a trick. And I've got another one of those for everyone today. So let's see what we have. We want to evaluate the integral from 0 to infinity of pi x times the hyperbolic cotangent of pi x minus 1 all over x squared, and then all times e to the minus pi x dx. So there's a lot going on there. But this actually simplifies down to a pretty nice number. And we're going to use three main tools, two of which have been proven on the channel in previous videos, and one that we'll do today. So the first is like a certain series expansion of the hyperbolic cotangent that says that pi times hyperbolic cotangent of pi x is equal to 1 over x plus 2x times the sum as n goes from 1 to infinity of 1 over n squared plus x squared. So that's a pretty cool result in its own right. Then next we've got the fairly simple integral which can be evaluated using integration by parts, which is the integral from 0 to infinity of e to the minus xy times sine y is equal to 1 over 1 plus x squared. And that holds when x is bigger than 0. That's because that gives you exponential decay here. And then finally, the result that we haven't seen on the channel before, but we will use, is this one. So it says that the sum as n goes from 1 to infinity of minus 1 to the n over n times si of n pi is equal to pi over 2 natural log of 2 minus 1. But what is si? Well, in fact, it's called the sine integral, and it's a function defined in terms of an integral. And it's defined like this. So the sine integral evaluated at x is equal to negative the integral from x to infinity of sine t over t dt. Now notice if x is equal to 0, you get a nice result that's related to the Fresnel integral, which we'll see during our calculation. Okay, so we're going to start with the following setup. And like I said before, we're working towards a proof of this last tool, which will be used for our main goal. So let's define the following function. So it's going to start off with a piecewise definition, and then it'll be extended periodically. So let's say it's equal to the natural log of x if x is between 0 and pi, not including 0 and also not including pi. Let's say it's equal to 0 if x is between pi and 2 pi. And here we'll include 2 pi, but we will not include pi. And then right in the middle, we'll define it to be the natural log of pi over 2. So it'll be like the average between those. That makes like a little half step between these. And this is exactly at x equals pi. So I think just by the behavior of Fourier expansion, this is not like totally necessary, but that being said, this will just make it a little bit more clear. Okay, so now let's do our expansion. Okay, but maybe before we do that, I'd like to highlight again that this is going to be expanded periodically with the period of 2 pi. Okay, so we can take f of x and rewrite it as a0 over 2 plus the sum as n goes from 1 to infinity of an times cosine of nx plus the sum as n goes from 1 to infinity of b sub n times the sine of nx. And well, there are some formulas for an and bn, but that being said, we're only going to need to calculate an because at some point, like a bit later, we'll be setting x equal to pi, which means that all of those terms will go to 0, so we don't need them. Which means that we might as well just not calculate the b sub n terms. Okay, so now let's recall how the a sub n terms are defined. So those will be equal to 1 over pi, and then we'll have the integral from 0 up to 2 pi of f of x times cosine of nx dx. Nice. But now check it out. We can really just integrate up to pi because essentially everywhere after that, except at a set of measure 0, our function is equal to 0. So we can write this as 1 over pi, and then the integral from 0 to pi of the natural log of x times the cosine of nx dx. Now let's notice that when n is equal to 0, something a little bit different is happening than the other cases. So let's work that case on its own. So we'll have a sub 0 is equal to 1 over pi, and then we'll have the integral from 0 to pi of simply the natural log of x dx. And we can calculate this a number of different ways. Perhaps we'll do it with a change of variables. So let's set t equal to the natural log of x, which means x is equal to e to the t, which means dx is equal to e to the t dt. Furthermore, if x is approaching 0 from above, we see that t will be approaching minus infinity. And then when x is equal to pi, t will be equal to the natural log of pi. So that maybe helps us do all of the stuff to transport this to a t integral. Okay, so now we'll have 1 over pi, then the integral from minus infinity up to natural log of pi of t e to the t dt. Now we can perform maybe tabular integration by parts on this. So we can make our little di chart. We'll put our polynomial here, our exponential here, take derivatives, take antiderivatives, and then match on the diagonal, and then alternate the signs. That's just a quick way of doing the integration by parts here, and that'll leave us with the following antiderivative. So we have 1 over pi, and then we'll have t e to the t minus e to the t, and we need to evaluate that as t goes to minus infinity up to the natural log of pi. But let's notice as t goes to minus infinity, both of those terms will cancel. So all we really need to worry about is what happens for natural log of pi. So that should give us 1 over pi, which is out front. And then here we'll have pi natural log of pi minus pi. So we've got something like that after plugging everything in. So I think that's pretty nice. But then how does that simplify? That'll simplify to natural log of pi minus 1. Okay, so that's our a sub 0 term. Now let's calculate the general a sub n term. Okay, so far we know f of x will be 1/2 natural log of pi minus 1. That's our a sub 0 term. And then we've got our cosine sum plus the sine sum. And the sine sum is probably not 0. That being said, we won't worry about it because we're most interested in the case when x is equal to pi. Actually, only interested in that case. So let's calculate these a sub n terms. So we need the integral from 0 to pi of natural log of x times cos nx. And we'll do this using integration by parts. So how might we do this? Well, let's take u and set it equal to natural log of x. That means our du term is 1 over x dx. And then we'll take dv and set it equal to cos nx dx. That means our v term is 1 over n sine nx. Okay, good. Now let's use our integration by parts formula. So we have this 1 over pi thing that's coming for free. And then we'll have u times v. So that'll be 1 over n times, let's see, the natural log of x times sine of nx evaluated from x equals 0 up to x equals pi. And then we'll have minus the integral of v du. So let's see. This will be minus 1 over n, and then the integral from 0 up to pi of sine nx over x dx. Okay, so that's where we're at. But I'm actually going to rewrite this a little bit. I'm going to take this 1 over n and bring it inside. And so we have sine nx over nx, just so that it looks a little bit closer to what we're going for. Now let's look at this limiting term. So if you plug in x equals pi, you'll get sine of n pi, which is most definitely equal to 0. Then if you plug in x equals 0, you get an indeterminate form. That being said, you can easily show that that will also give us 0 in the limit. So that means that this object right here is simply equal to 0. Which means what we have for this whole thing is minus 1 over pi times the integral from 0 to pi of sine of nx over nx dx. But recall that we're trying to get at this SI, or this sine integral function. So that motivates us to perhaps do a change of variables on this object, and that's exactly what we'll do now. Okay, so let's maybe take t and set it equal to n times x. Notice that means that dt is equal to n dx. In other words, dx is equal to 1 over n dt. Okay, so let's see what that leaves us with. We'll have now a 1 over n times pi out front because of this new n. And then let's see, we'll now have the integral from 0 to n times pi, just given this change of variables here, of sine of t over t dt. So we're getting close to this object right here, but we're not quite at it. Now I'm going to do this. Let's write this as, well, we'll still have this minus 1 over n times pi out front. And then next, we'll have the integral from 0 up to infinity of sine of t over t dt. And from that, we will subtract the integral from n pi up to infinity of sine t over t dt. Because now the differences of those two integrals is definitely this one up here. Okay, but notice this integral is well known. This is one of the Fresnel integrals. We've actually calculated that on the channel before. And this gives us a value of pi halves. And then this object right here, including the minus sign, is the SI, or the sine integral function, evaluated at n times pi. Okay, so that's good. Now let's maybe condense all of this. Well, actually, let's see what we have. We have our AN object is now equal to all of this. And now let's condense all of that and write maybe a closed form for f of x. Okay, so this is where we left ourselves off. We had f of x was this a0 term, and then that's our cosine sum, and then I just put our sine sum back in. And now we're going to evaluate this at pi. So let's see, we have f of pi is on the one hand equal to 1/2 times the natural log of pi, by our construction of this function f of x. But then on the other hand, it's, well, equal to all of this stuff where we plug in x for pi, or pi for x. So let's see. That'll leave us with 1/2 natural log of pi minus 1 for this term, and then minus 1 over pi times the sum as n goes from 1 to infinity of, well, we've got a bunch of terms without an x, so let's write those down. So pi over 2n plus si of n pi over n, and then cosine of n times pi. Oh, but cosine of n times pi is simply -1 to the n. That's pretty clear. Notice that cosine of 0 pi is 1, that's -1 to the 0. Cosine of 1 pi is -1, that's -1 to the 1. Cosine of 2 pi is 1, so on and so forth. So this gives us -1 to the n. And then all of this stuff, like we said, will go to 0 when x is equal to pi. So we don't really need to worry about that. Okay, nice. So now let's move some things around. So notice we can bring a 1/2 natural log of pi from this side to this side, and they'll cancel. And then we can bring this -1/2 over, and it becomes a +1/2. And then we can also bring all of this stuff without the sine integral to the other side of the equation as well. Okay, so let's see. That'll leave us with 1/2, and then we'll have plus the sum as n goes from 1 to infinity of, let's see, -1 to the n over 2n, but I might as well take a half out. Actually, I can take a half out of everything and I'll have 1 plus and then -1 to the n over n. Okay, so just to reiterate, that's from taking this term and this part of the sum over. Notice those pi's cancel kind of nicely. And then what are we going to be left with on the right-hand side after all is said and done? So we'll have -1 by pi, and then we'll have the sum as n goes from 1 to infinity of -1 to the n, the sine integral evaluated at n pi over n. But now I'm going to do a couple of things. Let's take this minus sign, turn it into a plus sign, then make this -1 to the n plus 1, and then we'll make this 1 into a -1. And then let's take this pi and multiply it through to the other side, and that gives us a pi in the numerator right there. Then let's see what the left-hand side is. So it'll be pi over 2. Oh, but then this sum is simply the natural log of 2. That's a well-known sum for the natural log of 2, the alternating harmonic series, minus the number 1. And then on the right-hand side, we have this alternating sum attached to this sine integral over n. Oh, but look at what we've got. We've achieved exactly this rule over here. Okay, so now armed with all of these three tools, we're ready to tackle our main goal. So now we're ready to go for it. So the first thing that we'll do is replace our hyperbolic cotangent with this sum expression. So let's see what that leaves us with. We'll have our integral from 0 to infinity. And then, well, we've got a pi built into this and this, so when multiplying through by x, this 1 over x will cancel to a 1, and then this 2x will build up to a 2x squared. And then we have our sum, as n goes from 1 to infinity, of 1 over n squared plus x squared, and then our -1, which is built in. And that's all over x squared, and then multiplied by e to the minus pi x dx. Okay, so that's applying this first rule. But we get a minor amount of simplification here. Notice that this -1 and this +1 will cancel. And then after that, this x squared and then this x squared will cancel. Then we'll rewrite this as, let's see, 2, and then the sum, as n goes from 1 to infinity, of the integral from 0 to infinity of e to the minus pi x over n squared plus x squared dx. Then next up, we'll factor an n squared out of the denominator. So I'll still have my 2, and then I have my sum as n goes from 1 to infinity. Now I'll have, like I said, an n squared factored out of the denominator, the integral from 0 to infinity of e to the minus pi times x over, now this is going to look like 1 plus x over n quantity squared dx. Okay, cool. And seeing it like this motivates a substitution. And the substitution here will be u equals x over n. Notice that means that dx is equal to n times du. Okay, and then the bounds of integration won't change because 0 over n is 0. Okay, so let's see. We'll have 2, then the sum as n goes from 1 to infinity. Oh, but look at this. One of the n's in the denominator will be gobbled up by this n times du, which the dx is giving us a single n in the denominator. So we have 1 over n. And then we'll have the integral from 0 to infinity of e to the minus, let's see, n times pi times u over 1 plus u squared du. And now we'll take this 1 over 1 plus u squared and rewrite it as this integral right here. So that's kind of the main trick at this stage. So I'll bring a bunch of stuff just across. So that means that I'm replacing this with an integral. So that's going to turn this thing into a double integral. Now we'll have e to the minus n times pi times u times e to the minus u times y times sine of y dy du. Now we'll change the order of the integration. And, well, I just have to copy a bunch of this stuff down. Okay, so that means my inner integral is now the integral of e to the minus n times pi plus y, all multiplied into u du, and then we can bring this sign out because that only depends on y. That's our outer integral. Okay, so now let's maybe see what this object turns into in the margins, because that's a fairly simple integral with respect to u. So that'll give us 1 over n pi plus y times e to the minus n pi plus y times u evaluated from infinity to 0, where I gobbled up a minus sign by changing the order of evaluation. But notice as u goes to infinity, this whole thing will be going to 0. So that means we don't really need to worry about that, meaning all we need to do is plug in u equals 0 into this. But plugging u equal to 0 into this will turn that into 1, giving us just that simple rational function. So in the end, we'll have 2, and then this sum as n goes from 1 to infinity, 1 over n, and then the integral from 0 to infinity of sine y over n pi plus y dy. And then let's do a substitution for this integral, which is inside of the sum, before we bring it up to the top of the next board. And the substitution will be to set t equal to n pi plus y. Notice that means dy is simply dt, but that's going to change our lower bound of integration from 0 to n times pi. So this thing is now going to be n times pi up to infinity. And then we'll have the sign of t minus n times pi over t dt. Okay, great. But maybe one last thing. Let's recall by the periodicity of sine, we'll know exactly what happens when we subtract off an integer multiple of pi. Well, it depends on the parity of that integer multiple. This is in fact equal to minus 1 to the n times sine of t. Okay, well, I think we're almost there, but that being said, let's start with a clean board. So this is where we ended up, but we're actually almost there. I'm going to take this and multiply it by -1 squared. I'm going to put one of the -1s right here, and I'm going to put the other -1 attached to this integral. But if we do that, then we've got exactly this SI function over here. And it's this sine integral function evaluated at n times pi. So that means we've got -2, and then the sum as n goes from 1 to infinity, minus 1 to the n over n, SI evaluated at n pi. Oh, but we've got a rule for that. So if we multiply this by 2 and -1, well, that'll cancel the 2 right here and swap the order of subtraction, leaving us with, let's see, pi times 1 minus natural log of 2. And I guess that's a suitable way to write the answer, but I think it's like a little bit more clever if you take this -1 and you write it as the natural log of e. And then we've got pi times the natural log of e over 2 using logarithm rules. And then we've expressed a closed form for our integral using two of the most important constants in mathematics, which, you know, adds a nice aesthetic to it. And that's a good place to stop.